Hello, and welcome to Chapter 2 of Math 103 for Gilbert Community College. In this chapter, we'll be going over variable expressions, what it is and how to use them. This will be a pretty quick chapter, and it is kind of the baseline for more complicated mathematics. It's the math that you actually do every single day, and hopefully some of the examples will help click that in a bit, right? All right, so with that, let's begin. So start with section 2.1, evaluating variable expression. So we're going to learn to evaluate a variable expression here. So what is a variable expression, right? We talked about this a bit last chapter. A variable is something that you do not know definitively. You do not know. 3 is not a variable. 3 is the number 3. It represents 1, 2, 3 different things, right? Or a group of a set, to use the words you used last chapter. A set of 3 things is described by the number 3. And a variable is when you don't know. Variables usually come in the form of letters, X, Y, Z, A, B, C, things like that. And those letters could also usually describe what you're talking about. The length of a side of something, you can use the letter L to describe length, for example. Radius, R, for example. And if you use those variables, those letters, in a math equation, we call that a variable expression. An expression has an equal sign in it. That's what that means. And variable has variables in it. The above shown equation is a variable expression because it has letters in it, right? And you can take these letters and you can figure out exactly what's going on and break it down as shown here below using the tools we used before. 3x squared is a variable, right? It is that. 2xy is a variable, it's there. And they're, swapping around, subtract x, or turning into positive, adding negative x, all the same thing, however you like to do it. So that is a variable expression. Variable expressions have elements in them that we call terms. A term is something that's separated by a addition or subtraction, essentially. So this here has, spotlight, there we go. This here has 5 terms in it. 3x squared is a term because it is separated from the 5y by a subtraction symbol. Again, if you have an addition or subtraction, that's how you separate out your terms. Notice here we have 5 different terms. 4 of them have variable terms because they have letters in them, or unknowns. And one of them is what we call a constant term because it doesn't change. It's constant. It is always subtract 7. Nothing touches that 7. So it's constant. It stays that way. We call it a constant term. Within those variables, we have what we call numerical coefficients, or the numbers, and variable parts, or the letters, right? The 3 here is the number that means 3 times. Hopefully you remember from last chapter when a number and letter are touching each other, butted up next to each other with no symbols in between them, that implies multiplication. And then the power here, we talked about those last chapter as well, right? The power is not a numerical coefficient because coefficient is multiplication or division. The 2 here is to the power of squaring it, right? Exponent. That's what that 2 is. But the 3, the 5, the 2, and the 1, or more specifically, the 3, the negative 5, the 2, and the negative 1 are your numerical coefficients of your variables, variable terms in this variable equation. This goes on, as I said, to division as well. It's the same song and dance. And we essentially, when I said at the start, this is the actual math you do, right? When you have a math problem, you're like, how many square foot of carpet do I need in order to carpet this room? That includes a variable. You don't know the amount of carpet. So the math you do in your head to solve for that, well, see, it's a 10 by 10 room, and I buy carpet in 1 square foot. So I need how many square feet? There you go. How many is that variable? And you could actually write that down as an equation by using a letter for that how many to solve your problems. In this example here, we have a W being a weight. and half multiplying by that W. So 1/2 W is our equation. If we say the W is 10, because of the question, then we replace that W with a 10, and then 10 times 1/2 is 5. Problem solved. Again, this is the math you've kind of always done. We're just giving you the definitions for that math at this point. Or we are evaluating a variable expression, to use big fancy math terms. So how do you evaluate something? Well, let's start with an equation. Let's start with AB minus B squared. There are two terms of that. AB is a term and B squared is a term. There's also two different variables in this equation. A is a variable and B is a variable. What that means is A and B can be different. Or actually, technically, A and B kind of have to be different in order for there to be an A and a B. Although they can be the same, depends on the question. Depends on the question, because the question answers it by telling us A equals 2 and B equals -3. So that means wherever we see an A, we substitute in or replace it with a 2. Wherever we see a B, we substitute in and replace it with a -3, or shown down here. See, they color coded them. Pink is A and B, and B is blue. Cool. So then they replace the A with a 2, and then in parentheses, they replace all the B's. Why do they do that? Because in parentheses is important. You care about that first. So since the negative is a very important part of that letter B, we need to make sure that negative sticks in that B, and everything we do to that negative, to that B, has that negative component to it. Again, this is important because we have exponents and we have subtraction here. So we need to make sure to follow our PEMDAS, or order of operations, at the top of every single math assignment you do until you memorize this. Write PEMDAS, PEMDAS. Write that down every single time. PEMDAS. To remind you, order of operations, otherwise you're going to forget it, and that's not what you want to be doing. So again, here's a worked out example. My suggestion when we come to these is to, when you get to this point, pause the video, solve it on your own, and then check your work. All right, that's what you're going to want to do, because this is really order of operations and variable exercises. And if you can't do order of operations, you need to get good at that, because all of math works off of order of operations. Cool. So we know what a variable equation is. Let's talk about what to do with them and the fun simplification rules in mathematics that can take very ugly looking math problems and turn them into very simple to solve math problems. We'll start with addition. What does addition mean? Well, addition with variables makes you care about the terms and what terms share common parts to them. For example, in the equation here, 3x squared plus 4 minus 7x plus 9 minus x squared, we have 5 different terms. We have 5. What am I doing here? There we go. We have 5 terms, but within those terms, we have 3 different types of terms, right? We have x squared terms, we have x terms, and we have constants. Cool. So what we want to do here is we want to figure out what those terms are, figure out what terms share on like terms in this example, and then we can actually separate them out and combine them to be useful. So what do I mean by that? Well, I see 3x and -7x are like terms, and I see 4 and 9 are like terms. So I can rearrange this if I want and put them together. Actually, I can do this with text, can't I? Yeah, I can. So all I can do is I can say, okay, 3x, over here, click, there we go. 3x minus 7x plus 4 plus 9 minus x squared. I can clump these terms together. What I do when I clump these terms, I'm skipping ahead in the slides a bit. What I do when I clump these terms together is I can use the addition and subtraction properties of variable equations to simplify or make there be less total terms. Because what is 3x? Well, that 3x, right over here, 3x is the same thing as saying 3 times x. Remember, multiplication is just doing something, doing addition, but writing it less complicated, because 3 times x is x plus x plus x. 3x's added together. That's what 3x is. So what is 7x? Well, 7x is the same thing as saying 7 times x, which is also the same thing as saying x plus x plus x plus x plus x plus x plus x, right? So I could rewrite my x terms that I clumped together as x plus x plus x. Oops. Get up here. There we go. X plus x plus x. I'm going to put parentheses around that because that's the 3x minus x plus x plus x plus x plus x. X. There we go. So the equation 3x minus 7x is, these are the same thing. Those are the same thing. Excellent. Now I can care about this jazz and I can do stuff with it, because these big, fun, nasty looking equations here can be resolved out. And again, I'm doing the super long form now to explain the idea. Once you understand the idea, you can shortcut this entire process and get to solutions much faster. So what is that subtraction symbol doing in the center? What is this dude and how does it relate to everything else? We touched on this. We touched on this last time, but essentially we're dealing with PEMDAS here again, right? Always can tell you, have it memorized, right? PEMDAS at the top of every piece of paper to remind you process. Parentheses happen first, then exponents, then multiplication, division, then addition, subtraction. So what we're doing here with this subtraction and then all these parentheses is we are taking a subtraction. We're trying to figure out how the subtraction plays with those parentheses, that 7x parentheses, or that x plus x plus x 7 times parenthesis. And if we think about it, we go back actually to the previous chapters here, the suggestion the book makes, and until you can do this in your head, do it, write it out long form, is you can distribute that negative number, or you can change that negative to a positive outside the parenthesis by changing everything in the positive to a negative on the inside of the parenthesis. What am I doing when I'm subtracting 7? I'm adding 7 in the other direction, right? Think about your number line. Oh, you drive a, I do. Oh, cool. Right? You got your number line here. So if I'm subtracting 7, have that be 0, 1, 2, 3, 4, 5, 6, 7, right? Subtracting 7 means adding 7 in the other direction. So if this direction is positive, the opposite of positive is negative, which means this direction is negative. So it's, instead of adding x 7 times in the right direction is positive, if I subtract 7x, I'm moving 7 times in the negative direction. Or in these terms here, let me just move this out of the way a bit there. So I still have my x plus x plus x here, but then I can essentially add a negative x minus x minus x minus x 4, 5, 6, 7. I can do that, right? And again, what I'm doing here is I'm saying, and I'm adding 7 left steps along the number line, or I'm subtracting 7 x's. They're the same words. And this is useful because I've essentially solved my parentheses, so I can write this out without parentheses, plus minus x minus x minus x minus x 4, 5, 6, 7. And then what happens if I move to the right 1x and I move to the left 1x? I did move, right? So I essentially am allowed to, for every positive X and negative X combination, I don't move. I move forward one space, I move backwards one space. So those, we say in math, cancel each other out, leaving me with, as shown here, let's move this down a little bit. I've gotten rid of all my positive X's. I only have negative X's left. I have how many? 4 negative X's, right? Which is the same thing as saying minus 4X. Cool. So let's do one more text box down here. I can also ask you, what is 3 minus 7? Well, that's the same thing as saying that little equal sign with the arrow next to it means like, it's not an equal sign, it's the same thing, essentially. I can't remember the actual term. That same thing as saying 3 plus negative 7, which is the same thing as saying 7 minus 3. Oh, sorry, no, yeah. 3 plus negative 7, or 3 minus 7. It's not 7 minus 3. I screwed that up, sorry. But what does that mean on the number line, right? Well, we move 3, let me erase these here to 2, add a couple more here. Again, I'm going over this in super detail. If what I'm doing, you're like, I don't need to do this, whatever. I get all this already. Fantastic. Feel free to skip ahead in the, I mean, if you can do the homework without needing these videos, do the homework without needing these videos, believe me. So let's say this is 0 here. So 3 in the positive direction is this way, 1, 2, 3. And 7 in the negative direction, 1, 2, 3, 4, 5, 6, 7. 7 in the negative direction lands me right there. What is that? That is negative 4, right? We move 3 steps forward, 7 steps back. So 3 plus negative 7 is the same, is equal to negative 4. And if we did this with all the x's, we get negative 4x. Long story short, 3x minus 7x is equal to minus 4x. I hope showing it super blown up like that makes sense to you and connects a bit. Because once you get this down at a automatic level, you understand these rules at automatic level, this stuff becomes super easy. And then take what we just did with the x's and apply that to plus 4 plus 9. Meaning we can simplify this entire equation out. I'm going to clear everything. We can simplify this entire equation out, once we know what we're doing, to be negative x squared, and I'll explain why we're rearranging terms here in a bit, minus 4x plus 13. The big equation here, this is the same thing as that. Same thing. Instead of having 5 terms, now I have 3 terms. And that's what combining like terms means. Distributive property is a way to care about multiplication in like terms. And shown here is an example of that. If we follow PEMDAS, again, write it out until you have it memorized. Come here, you. There we go. PMDAS, PEMDAS. We keep that in mind. We can look at an example here of 2 times 3 plus 4. PEMDAS says we need to evaluate the parentheses before the multiplication and multiplication before the addition, right? Within the parentheses, we have addition, so we need to solve that first. So 3 plus 4 is 7, and then we can do multiplication. 2 times 7 is 14. However, we can use the variable expression and the properties of addition, stuff like that, to rewrite these equations out. Because if we have a 2 on the outside, that's what we did before with the subtraction symbol. We can distribute that through because it's saying we have 2 copies of what we're doing here. So I'm going to write this out long form over here as well. I think the long form usually helps. So this is saying we have 2 times the quantity 3 plus 4. What is 2? Well, 2 times is adding the same thing twice, right? So we have 2 copies of 3 plus 4 that we are adding together. Excellent. So that means we have 3 plus 4 plus 3 plus 4. We can clump those together, say 3 plus 3 plus 4 plus 4 if you want. We can just rearrange it, it's addition. It doesn't matter, which is the same thing as saying 2 times 3 plus 2 times 4. 2 times 4. You see what we did there? We can rearrange things because it's addition. Right? If you have 4 fingers on one hand and 5 fingers on the other hand, that's 9 total fingers. If you swap your thumbs, have 5 fingers on your left and 4 fingers on your right, you still have 9 total fingers, right? Addition doesn't matter which way you add it together. But the distributive property shown here allows us to rewrite this basic question in many different ways and achieve the same result. This is all adding up to 14 eventually. Here we have essentially 6 plus 8. Here we have 7 plus 7, all the same thing. So try doing the lower one by yourself, pause the video. When you come back, make sure you did it correctly. So the real use for the distributive property is, as I said, the variables. So if we look at let's look at the top one here. If we have 2 plus 3 in parentheses times x, we can solve that by PEMDAS, which is, so there we go, 2 plus 3 x. That's the same thing as saying 5x. The parentheses is solved, so we can just write 5x. Cool. Or we can go here, distribute that x. So we say send it into the parentheses because, again, that's how the distributive property works. Just showed you example this last time. Just say 2x plus 3x. Well, now we can have like terms, so we can add those together because that's plus x plus x plus x plus x, and we have 5x's there, so we can just chop that down to be 5x. Many different ways to attack the same problem. So given that information, there we go. Oops. Given that information, look at the bottom one, pause the video, solve it on your own, come back. Associative property is the thing I was talking about before. When you're adding things, even if they have parentheses, if it's all addition, organization doesn't matter. That's what's going on there. Communicative property, similar song and dance. If you're adding stuff together, organization, again, doesn't matter, be it with parentheses or without parentheses, because addition doesn't have, addition doesn't care about organization. Anything to 0 is 0. We know this already. Skip through a lot of this stuff. Adding and subtracting the same thing from itself results in 0. This is the example I did before. If I move 3 steps forward, then move 3 steps back, I haven't moved. Right? And a lot of these seem obvious and kind of dumb for me to go over. I get that. But these basic ideas of math do a very good job of being important when math gets more complicated. Because this adding the opposite to equal out 0 is canceling. That's what canceling is. And when you get to higher mathematics, you're going to hear, oh, cancel this, cancel that all the time. That's the reason. So take a little bit, try this example on your own at home, and make sure you get the same result. And if you don't, you need to let me know so I can work on something more in depth with you. Here's another example for you to try at home. Right, so let's dive into multiplication here. Multiplication is very similar to addition in that, by and large, the organization of the multiplication doesn't matter. When you're on the multiplication step, you've got a lot of things that multiply together. Go ahead and multiply them together however you want. Parentheses don't really matter when we're multiplying stuff. as you can see with these examples here. I'm not going in depth here. I think that these examples are best done to learn versus me talking about them, which is why I'm again going through them quickly. Multiply anything by 1, you get the same thing. And division, as I said in the previous chapter, is the opposite of multiplication. In this slide, we use the word reciprocal. The opposite of A is 1 over A. And multiplicative inverse, if you really want to get fancy, impress all those friends at the bar. But yeah, so if you have something, 1 over itself is its opposite. And then when you multiply something by its opposite, you get 1. Example shown there. Again, when we start applying this stuff, you're going to see its usefulness. There's a simplification example. Again, I'm not going to keep hopping on this concept or go over these examples because you need to be the one writing this stuff down and practicing this concept. If you're not writing this stuff down and practicing this concept, what's the point of doing that? You're not going to learn it by me just talking a bunch, right? I'm giving you work through examples. You need to work through them. All right, last thing, distributive property. Here's, we talked about this before. If it's on the outside, it applies to everything on the inside. Noteworthy for this example, we're doing multiple rules, one after another, because we're distributing the 3, and then we're also distributing the 3 again, right? The 3 here is distributed throughout, and then this 3 is distributed to the 2x. Yep. I want you to do these examples. If you got this stuff down pat and you're like, I don't even need to look at it anymore, skip on ahead. Go to the homework. That's cool with me. Here's a pretty complicated variable expression that is, I think, worth your time to stop and try to do. It's worked out here for you, which is nice. Essentially, what we're doing here is I'm giving you lots and lots of annoying subtraction symbols, and you need to figure out what to do with them. The place that's going to trick you up is probably these dudes. Why did that become this? If that's confusing to you after the fact, I need to know that. And if that's not confusing to you, then fantastic. Move on. Right? Another example. And then let's get to verbal expressions into variable expressions. So the meat and potatoes of all this, how do you actually use stuff? We talked before about words that mean math. We gave examples of this: addition, subtraction, multiplication, division, and exponent. Essentially, if I say you're adding things together, that means you're adding things together, right? Or increased by is addition. So knowing when these words show up, what they mean in math is what allows you to do math in the actual real world, right? Translate the phrase 14 less than the cube of x into an expression. That's a very dumb sounding sentence, but that means something in math. And someone might say that in a factory or in a hospital or something like that. So you need to understand how the words translate. Noteworthy here, cube of x. Cube means raised to the 3rd power. So the cube of x is x to the 3rd power. I have a 14 here, so someplace I got a 14. Less than is subtraction. So is 14 less than the cube of x mean x to the 3rd minus 14? Or does that mean 14 minus x to the 3rd? Because the sentence is the 14 first, right? Well, that's where you got to stop and think about it. Less than is the 14 subtracting off from it? Is the 14 the primary one in that sentence? Or is the cube of x the thing I care about? Because these are not the same equation at all, right? If x gets really big, if x is really big, this is a positive number. If x is really small, this is a negative number. So if they are not in the same equation, you need to know which is which. Think about what you could be describing with 14 less than the cube of x to determine which of those two equations best fits. Here's another example, the total of 3 times n and 5. Total is addition. Let me go spotlight here. Total is addition. What is being added? Well, you got 3 and n and a 5. How do those relate to each other? 3 times n tells you how 3 and n relate to each other. It's multiplication. That leaves a 5 out here without a word next to it describing the mathematical concept. So that's why you have to go back to total, care about that total. Well, that's where the mathematical concept comes from. If you don't know what an equation means, slow it down, write it out, figure that stuff out long form, right? This is figuring it out long form. Until this stuff is obvious to you, it's not going to be obvious to you. You need to practice that. So let's look at another example. Translate a number added to the product of 4 and the square of the number into a variable expression. What does that, all that jazz mean? A number added to the product of 4 and the square of that number. Well, a number is a variable expression because we don't know what that number is. We just know that's a number, right? So we pick a variable to describe a number. We call that n. Cool. What's the square of a number then? Well, the square of a number is the square of the number. Cool. So a number added to the product of. I have added to and product of. Added to is addition. Product of is multiplication. A number added to the product of 4 and square of the number. So product of 4 and the square of the number, that's the way the product defines. I got a lot of junk here, don't I? There we go. So the product of 4 and the square of the number. So that's multiplication, which is where this comes from. And I'm adding a number to that thing I made, which is how we get to this point. It's confusing. It's also important. Sorry. So here's some examples, word problems essentially. The height of a triangle is 10 foot longer than the base of the triangle. Express the height of the triangle in terms of the base of the triangle. Okay. So I have variables here because I don't have the height or the base, right? 10 foot is not describing the height or the base. It's describing the relationship between them. So what do I do here? Express the height of the triangle in terms of the base of the triangle. Well, base of the triangle, I can call that B. Height of the triangle, I can call that H. That makes sense. Cool. So what do I know about these things? So I know the height of the triangle is 10 foot longer than the base. So whatever the base is, the height is going to be that base plus 10. Because the height is 10 foot longer than the base. Longer is addition, right? It's easy. It's if the me saying it that way makes it sound it is not providing you with enough information, then again, I need to know this so I can go slow and more in depth with you individually. There's a good chance a lot of people taking this class, this is obvious things. You can finish the homework without having to watch this video. Fantastic. Comment or shoot me an email if you need to know more. That way I can spend time working with you on it. The length of the swimming pool is 4 less than 2 times its width. Express that length out. Pause the video, try to solve it, make sure you get the correct answer. If you don't, let me know. You don't want to be running into these issues on the homework when it's due. You want to be running into these issues when you're practicing beforehand. And that's all I got for chapter 2. That's a pretty quick chapter. We're really just building the foundation to do math. You need to understand how a math sentence combines. You need to be able to create a math sentence before you solve a math sentence. Chapter 1 is the nuts and bolts. Chapter 2 is the foundation. Moving forward, we can actually start presenting problems and having you solve them without me worrying about you getting lost in the trees, right? That being said, thanks for watching. Shoot me a comment if you have any questions, send me an email, and take care.